And now it's time to turn to our guests. So Professor Kent Schwitkis and the Astronomy, Physics, and Engineering at Compton College and the STEM Club there. Welcome to All Space Considered. We're thrilled to have you as guests tonight, and I can't wait to hear what you and your students have going on.
Well, thank you very much for inviting us, and we're pretty excited to let you know just what we've been doing. The starting off of tonight's presentation by you folks actually was a compilation of 3 minutes that one of your folks did of 9 hours plus of videos that we took on our last balloon. So we really appreciate just that input that we've gotten from you guys. So this is really a story of all of the things that we're doing. So, you know, we have a picture here of us together, of launching the balloon, and we have other activities going on as well. So the first thing I want to do is introduce the students that are going to be speaking to most of the charts tonight. I'll be doing a little bit, but mostly this is their thing. So Arrington, would you start us off, please? My student voices need to unmute themselves.
This is a common. It's a common problem for even us All Space Considered veterans. We forget to unmute ourselves all the time. So welcome to the club.
Hi, everybody. My name is Arrington Mitchell. I'm a current Compton STEM Club president, and I'm a chemical engineer major at Compton College.
Hi, I'm Vanessa Armenta. I'm currently a Compton College student. I'm the vice president of the STEM Club. I graduated in communication studies in CSULB and minored in public relations, and currently pursuing my computer science degree, master's.
Regina?
Hi, my name is Regina Washington. I'm a current Compton College student, and I'm majoring in geology, and I'm minoring in computer science. I'm also a business entrepreneur.
Okay, Jamie, would you?
Of course. Hi, my name is Jamie Alvarez, and I'm a past Compton College student and the past STEM Club president. I'm currently at Cal Poly Pomona, and I'm majoring in mechanical engineering.
Trey?
Hi, everybody. My name is Trey Willingham. I am currently a physics major at Cal Poly Pomona. I am an alumni of Compton College, and I was a former STEM Club president.
Now, Regina is going to roast me. You guys can see my background. It's I'm old, as you can tell by the gray hairs, but Regina wanted to roast me, so go and roast me.
Hi. Always tell me they have a problem with gravity, but I told them, just drop it. Hi, folks. My name is Kent Schwitkis. I'm currently a full-time professor at Compton College. I've been teaching physics, astronomy, and engineering for the past 8 years. I love teaching students, allowing them to have an open mind and explore the universe with the abundance of matter and energy in many different forms. Teaching is my second gig, if you will. I was an aeronautical engineer for Boeing and Hughes Aircraft for 25 years. You would think I have physics down by now, right? Okay. I've written 45 publications, with one is still in circulation. I have written over 45. That's cool, right? I have 3 degrees, one of which is a PhD, which allows me to defy gravity. In my free time, I enjoy star parties, hiking, helping other people, volunteering on and off campus, going to Joshua Tree, and conversing with
Okay, thank you for the.
What is Compton College? Located in Compton, one of the oldest community colleges in the state. It started in 1927. Full-time 1,400, part-time 6,000. As you can see, one of the little red dot is where the school is, and the other dot is where the Griffith Observatory is. The demographics. College and community college are pretty much the same, as you can see in the city demographics and the school demographics. Our school has 2/3 Latinx, STEM transferees demographics. They transferred to other schools.
When we speak to major points of the program, some of the more unique things about Compton College is they have a program that's set up to, matriculate under the community college students into higher education. And this is done by intensive mentorship and a lot of outside activities to merge the material learned in lecture so that students get more practical applications, such as you'll hear about the Make It Happen project, where students get familiar with Arduinos and coding and sensors. You'll hear about biology projects where we have a greenhouse project. And you also hear about big things like the rocket, the Compton Common, which is a 20-foot long bipropellant rocket. And one of the more unique things about Compton College is that these are opportunities that you wouldn't find they're not widely available at the regular community college. And so these are opportunities that I'm finding and I see at Cal Poly Pomona right now. And that's what, to me, made Compton unique. And you also, what I found out is that most of these projects have hundreds of people working on them. There's many students involved in different subsections of the rocket, and everyone's putting in their work. Here, it's a small subset of us, and we're working intensively with our mentors. And that engagement, I think, is what is really, really unique to this Compton College.
The STEM Club. It started in spring 2019 as the Cover for Weather balloon project. We have organized, influenced different various projects, which we will be talking about later on. We meet every Friday, even during intersessions. COVID really snapped the growth, but we're getting more and more members.
Some historical activities that we've done throughout of Compton STEM's history is our weather balloon, or our HAB, which is our high altitude balloon. The Compton Common, as noted before, which is our 20-foot liquid fueled rocket that I'll be speaking on later on in this presentation, and different gravity experiments. And we're specifically observations of the drag crisis. Other activities that Compton STEM Club is involved in is, for starters, the Make It Happen project. The Make It Happen project is a program that we started in order for our club members to stay engaged when COVID struck us, and for us to have hand-on engagement in the on Zoom and hand-on and engagement between the students and Zoom. I was a part of the first group of Make It Happen project, where we used Arduino kits to code different programs, and we actually, and part of my group, we coded a robot to actually be an alarm clock. My vice president, Vanessa, was also a part of Make It Happen in the second wave. And Vanessa, you want to speak on your experience in the Make It Happen project?
Yeah. For the second one, we built a robot car, which we got to assemble it. And once we learned a little bit of what it does, we got into groups where we did a competition of who can finish a maze the fastest and more efficiently. In that maze, there was a bridge of death, which was taken off of the Netflix program, Baking Impossible. What my team did at the very end, we were able to have like a code of anything we wanted just to make our robot stand out a little bit. So what my team and my group did is we made the robot dance.
We also have star parties throughout the year. The last star party that I was personally involved in happened in September, where we went up to Joshua Tree National Park and got to observe different constellations and stars and planets. And I was also a presenter, and we also as a team manned 3 different telescopes during the observation that night. We also have various different rocketry projects that we've been working on throughout the history of the club, as noted before, and will be discussed later on this presentation. And last but not least, we have biology projects. We actually have a greenhouse on the Compton's campus, where we grow various different fruits and vegetables and plants in the greenhouse that we have.
So before COVID hit, the STEM Club had various partnerships. One of the partnerships was with Loyola Marymount University. We tried to create a partnership with them to obtain guidance on rockets, since our club was starting its own rocket. However, due to logistics, this partnership did not work. However, we were still able to visit their campus and sit through a design review as customers for their CubeSat. There was even an offer to use our high altitude balloon as a platform to help launch their CubeSat. But again, due to logistics, it didn't happen. Another partnership that we tried to create was with Chapman University, but due to COVID, that fell through. However, we're currently working with the math and science prep and helping them launch their own balloon, since they reached out and asked for advice. So the STEM Club is tutoring them. So I'm going to be talking about our big project at Compton College done by the STEM Club, which is the high altitude balloon. We were able to successfully launch our high altitude balloon twice, one in 2018 and 2019, in coordination with the FAA, which is the Federal Aviation Administration. During our 2018 launch, we had a few problems with our payload, but due to our power supply failing after an hour, our payload was only partially working. Another thing we discovered was that our SPOT and APRS transmitter didn't collect any data over 12 kilometers of altitude. I'll explain in a later slide how we fixed these problems. Even with these hiccups, we were able to land near Victorville, which was 10 kilometers of our prediction. Now, during our 2019 launch, we still had a few hiccups with our payload, but we obtained far better data than in 2018. This could be due to the fact that our mentor, Professor Villalobos, motivated us with a trip to Benihana's for lunch if we were able to reach a certain altitude and obtain good data, which we did. Our payload worked at 90% with 3 hours of video footage and with most of our sensors collecting data. We successfully reached an altitude of 32.2 kilometers, but please note, even if we reached our altitude and collected sufficient data, we are still working to improve our balloon. So I'm going to talk a little about the 2019 launch first, because it was very publicized. We appeared on Channel 2, and I just want to emphasize that for our 2019, just as Steve Morgan said, we have data, which is organized in the chart you see here at the bottom. A quick summary of what was in our payload. We had 3 cameras that were facing up, down, and sideways that collected 3 hours of video footage each. We had sensors both inside and outside of the payload that were set up to have a 10 degree of freedom, which gave us 11 axes of data. We also had 2 transmitters in our payload, which are essentially small GPSs that tells us where our payload is. Okay, now we'll be talking about the flight simulation for 2018. For this simulation, we used a website that allowed us to predict where our balloon will fall using a few variables, such as weight of the balloon and estimated temperature of the day of flight. As you can see, the simulation and our data were both very close. Both GPS receivers gave out similar results from beginning to end. I do want to point out certain times in our SPOT transmission data. At 2:25 p.m., our SPOT transmitter goes dark, and it takes about an hour to receive a location from it. It then shows that at 3:53 p.m., the balloon hits the ground, and then we send our retrieving group to go get the payload. Then we get another ping around 6:03 p.m. that shows the balloon was picked up. However, it stays in the same location until 6:30 p.m. The reason was that our retriever Brian got stuck out in the mountains due to fear of heat stroke, so the fire department had to go and rescue him. But thankfully, both him and our payload were safe and sound. Now I'm going to talk about the 2018 altitude analysis using the APRS data. I would like to point out a few things on the graph first. The yellow line represents our temperature data, the gray line represents our simulation, and the blue line, that is short, represents our APRS data. As you can see, the transmitter did not report anything above 12 kilometers of altitude, and it was later known that it was due to not having the proper chip. However, this didn't stop us. We created a modified version using the blue line as a guide. We said that if the balloon stayed at a constant altitude, then it could reach an altitude of 27 kilometers. Please note that this was a speculation. We also used data collected from our cameras to obtain this altitude. It was done by using Tejon Pass Highway as a pinpoint because it was something we saw through our camera. With the angle, we were able to tell our height. So for this slide, I will be showing the superposition of 2018 and 2019 altitude data. As you can see here, our yellow line is the 2019 altitude, which was 32.5. This was obtained due to our functioning APRS. We had a few issues with our spot, but we will describe those issues later on. Now to our orange line, which is our modification for our 2018 altitude data. As you can see, our blue line is our actual data collected, and the orange is our estimate. And we estimated to have reached an altitude of 25.9. As you can see, both times the shape remained the same, which gives us the credibility to our 2018 estimate altitude.
Okay, I guess it's my turn to talk now. They've done so well, I wish they would continue. But this is our ground track for 2019. The ground track is on the left-hand side and the predict is on the right. And if you look carefully, you'll see that the difference here is about 35 kilometers. We didn't quite match up everything, although you can see the general trend is the same in both. The simulation that we use to get the ground track is based upon current weather data, the one that we like to use, and it does a really good job of doing the prediction. And the one that we had to use in 2019 was not nearly so good. So we had some issues there. One thing to note, though, is we had we got our recovery team system down better. As mentioned before, we're trying to always find better ways of doing things. So this time we had a couple of cars going out to retrieve the balloon. They were basically following it as soon as the balloon was launched. As an indication of this situation, it took only 30 minutes between when the balloon hit the ground and when they picked it up. Now, one of the other things that we've been alluding to is that we can make things better. And one of the things that we found out this time was is basically we had an issue with entanglement of our parachute lines when the balloon burst. So what that meant is indicated on this graph here on the left-hand side. This is the ground track as reported by both the APRS radio, which requires a ground antenna. It needs to see a ground antenna similar to your cell phone. And you can also see superimposed upon it the orange dots, which are the spot, which is the spot, which only goes up to 12 kilometers of altitude and then turns off essentially. And it is looking for satellites. So the timeline that I want to point out here that I want to concentrate on is at 3 o'clock, the APRS turns off at about 3 kilometers of altitude. So basically it's no longer seeing if you will, a cell site. At 4 o'clock, the spot turns on. The spot turns on, but it doesn't tell us where it is. It takes another 10 minutes for the spot to give us enough data to tell us where it is. So the ground team can find out from the control team where they should be going. Okay, so, and then it took then there was another 5 minutes and the actual balloon hit the ground and we didn't see any movement. And then finally you can see the spot reports new movement at about 10 minutes to 5 o'clock, indicating that the balloon got picked up. Now, this is one of the pictures that we have of the balloon. If you recall the opening credits, shall I say, or the opening video which contain the balloon bursting. If you look carefully at it, you'll notice, if you played the video, you would notice that one of the boxes which we had for a payload, which was the bottom box, turned out to be above this box, which has the video pointing at the balloon. With all the chaos that's resulting from the balloon bursting, somehow bottom became top and top became bottom. And we figured that caused some entanglement, and that can be observed in this chart on the right-hand side, which is a plot of the velocity of the two campaigns. The velocity in the second campaign, the 2019, is almost twice that of the first campaign. So that's something that we want to correct in the future. Okay, this is, as was spoken about before, we took a bit of data. The left-hand side is pressure versus altitude. The altitude is in orange. And as you see, as you go up in altitude, the pressure decreases, and it's following the power law expectation that we would have for an atmosphere. The other plot on the right-hand side is evidence that we've actually gone into the stratosphere. So this is a plot of temperature, which is in blue, and it's also against the orange, which is the altitude. So as we're going up in altitude, then as we're going through the troposphere, we're decreasing in temperature. And then right here, we're actually entering the stratosphere. And you can tell that because as we go higher, the temperature increases. Then the balloon bursts and the ultimate reverse occurs. We're falling, therefore the temperature is falling until we get into the troposphere, and then the temperature starts rising again. Okay, Regina, could you tell us what we're going to do next?
Moving forward, we would like to improve the design of the high altitude balloon. First, we would like to consider using a balloon, which is a balloon and parachute like a braking device, most effectively used in high altitude and supersonic velocities. The balloon will decelerate, stabilize, and have more air resistance for the payload to land in an upright position. The second idea is to increase the distance between the balloon and the parachute. Secondly, we would like to include a first aid rider in each recovery vehicle for the safety of our members, our team members. Next, we would like to record sensor data both inside and outside the payload box. Last but not least, we would like to include the light intensity and comic ray sensors in our sensory suite.
I'll be speaking on the rocket programs that we have been doing in the Compton STEM. So we started off working on water bottle rockets, and then we started moving our way up to Estes type and predicting landing sites, and made our way up to Alpha 5 feet rocket. And now we're currently working on that 20-foot liquid bipropellant rocket using the base 11 guidelines for colleges building a rocket, and that's the guidelines we're using to build this Compton Common rocket.
Okay, so I'm going to speak to this a little bit. One of the primary goals here is to do some analysis and show our students that even with rockets or Estes rockets or these alphas, which are 5 feet long and go a mile up in the atmosphere, that you can do analysis on them and find out some interesting things. This is the initial analysis, and you might notice right away here that once the propellant is all used up, we ought to have an acceleration that matches the acceleration of gravity, minus 10 meters per second. And what we see in this, if you can read this, it's like minus 200. So there's something else going on there. And basically most of it is taken out because we haven't included parallax. So as you get further away from something, it appears smaller. So when you account for that, we get a much better deceleration, if you will, of when the rocket has exhausted its propellant. It's still not entirely correct. As you can see here, we've got a deceleration of about 24 meters per second, and that's roughly a factor of 2 more than what we would want. Arrington, you're muted.
Sorry. So the Compton Common is the name that we give into the rocket that we're currently working on. Some of the components of the rocket is that we're working on a simulation for the rocket where we're using the Monte Carlo system to factor in different parameters and input our parameters as we come closer to launch day to see how the rocket will play out and calculate our velocity and our descent times and our run time. Currently, we're working on plumbing up the rocket. So we're working on putting in all the connecting tubes for the rocket fuel down to the rocket engine. So our current to-do list is continuously working on our simulation that we have bi-weekly on Wednesdays every month. Our next objective is to hydro test our tanks and to also fill them with liquid nitrogen so we could test how they would do under a cold setting. And then our last but not least, we'll be working on the skin of the rocket, which is the outer shell of the rocket for the entire length of the rocket.
Okay, I get to talk about gravity. So I've had the pleasure of working jointly with Professor Schwitkis on a gravity analysis. Particularly though, we look to observe the drag crisis. So this was intended so that students can experience the material as close as possible, become more intimate with it by doing more hands-on things. The drag crisis, for those who aren't aware, it's associated with when you have laminate to turbulent layer flow at a boundary adjacent to the object. So you have a buildup. So we use a software called Tracker, which analyzes videos. And so what we did is we analyzed objects for falling through air, and then we extracted the data and plugged it into Excel. This process helps students become more familiar with the numerical integration process and dealing with issues of parallax, as Professor Schwitkis had mentioned before. One of the famous lines we had during our process was, buildings don't move. So now we're looking at the graphs. You have a correlation, a residual, and a fit. The equation that you saw on the last slide was actually what we use for the fit, and it's overlaid with the data. And for those who aren't familiar with the residual, it's just the difference between the data and the fit. And throughout these simulations, we assume for the drag coefficient to be constant. But as you can see through some analysis here, we have a systematic error in our drag coefficient, even though we have good correlation between the fit and data. So, and just worth mentioning, the last set of graphs are for the videos that we're analyzing the beach ball. These set of graphs are analyzing the medicine ball. And we see sort of the same correlation going on here on both of the graphs with the overlays, except for in this one, we did get a better fit to the position to data and also to the velocity to the fit to the data. But we still have much work to do.
Okay, so yeah, the only thing I would add to that is with the beach ball, you would expect the drag crisis to occur. The medicine ball is really pretty heavy, and so air resistance isn't play much of a role. Okay, so there is we're almost done with this. There are a number of people that have helped me. As we mentioned, Lorena Fonseca, who's with us now, has helped us a lot. Brian Johnson, I'm elevating him to a co-crazy person. We rode our bikes together to Boeing nearly every day, dodging all the errant drivers around. And then we have also I'm also including Waldo Stakes, who is helping us with the Compton Common. Dave Nord is currently running the Compton Common. He's the lead so-called adult. And naturally, I couldn't continue with this if I didn't have a break in teaching after I stopped working at Boeing and Hughes Aircraft by Dean Arvidsson, and of course my PhD advisor. So at this point in time, if there are any questions, we will, we'll try to answer them.
Yeah, wonderful job, first of all. Let me give you guys a round of applause. So awesome job presenting what you've been doing about launching balloons and the rockets. And also, I didn't know about the drag crisis. That was interesting to hear about. There were a few questions that were asked in our chat, our YouTube chat, which people, by the way, are congratulating you in there and saying, go Compton College STEM Club. So you've made some fans in the YouTube chat. But folks want to know, when you're making the rocket, how did you make the components? Are they 3D printed? Are they machined? How are those being created?
Yeah, go for it, Trey or Arrington.
Yeah, I could speak to that. Majority of our components that were used on the rocket, we've gotten from surplus. So we have a very advantageous mentor, and he likes to go out and take us places and kind of learn how to use our resources rather than having, we don't have a very wide budget per se.
Okay, yeah, well, that's great to be able to have folks to provide things that you need. Now, are you planning on launching any more balloons? That's a question I have.
Yes.
Yes, definitely. Another balloon is in the making as we speak. We're actually getting the parameters together and starting to divvy out the job tasks and organize the event. So you can definitely see a HAB balloon in the future.
Okay, great. Because I'd like to hear more about that. It'd be fun to see the footage from that and the data.
Our target for that is, again, June of this year, late June.
Okay. So this year, wow. So you're that seems difficult to do with everything that's going on in the world. But then again, when you've got a team like you have, you can get things done, which is really terrific. So somebody wanted to ask, is there Compton scattering in physics? So that's a physics question. Do you guys know about Compton scattering?
Well, we don't perform it on campus, but yes, there is Compton scattering. It's a different Compton. I forget the area's name and the school are a different Compton than the Compton for Compton scattering.
Okay, and I would suppose it's different than the Compton X-ray Observatory as well, which was probably the same Compton as the scattering. So, but you'll create a whole new famous Compton with the work that you're doing.
Hopefully.
Exactly. Well, folks, thank you so much for joining us tonight with this fascinating discussion on your on the project you've been doing. And also, I just want to compliment the roasting of Professor Schwitkis. I thought that was very brave to do with your professor there, but it was quite funny. So.
Let me point out that the wig and the mustache, what you see now is very much shortened. I have been approached and asked if I am Santa Claus.
Oh.
Well, there's time to grow that back before that season rolls around, and you might want to, because it could be a good look. Well, again, thank you so much for joining us tonight, and it's always wonderful to hear what local STEM clubs are doing, especially when you're doing things that are really shooting for the stars. You're really going for it. So congratulations with your club and everything you've been doing, and keep on with the engineering and science, and keep us informed here at All Space Considered. We'd love to know what you're doing and when you're doing it. So thank you for joining us.
Thank you.
On behalf of the STEM club and all its members and faculty, thank you for the opportunity.
You're absolutely most welcome. And again, awesome job. Congratulations, everybody.